Hello everyone, my name is Oscar Macias. I currently hold a joint postdoctoral position between Carly IPMU and GRAPPA. And for this contribution, I'm going to highlight our recent results in which we study the sensitivities of the upcoming Cherenkov telescope array to the high energy tail of the galactic center excess. Further details about our work can be found in this archive identifier, and our paper was recently accepted by the journal MinRAS. All right, without further ado, let's start. Observations of the center of the galaxy with the Fermi-Lab telescope have revealed an excess emission above the astrophysical background. Interestingly, this excess has been confirmed by many independent research teams, including the Fermi-Lab collaboration. The current consensus in the community is that this excess is not a statistical fluctuation of the astrophysical background. And the hypotheses, the two main hypotheses that have been discussed are either a large population of millisecond pulsars in the center of the galaxy or a dark matter self-annihilation signal. Now, a very powerful argument that we have made in the recent papers is that the spatial morphology of these two hypotheses is expected to be different. Since millisecond pulsars are very old stars, they are expected to follow the spatial morphology of the old stellar population in the galactic bulge, which we know follows the triaxial boxy bulge morphology. While for dark matter, different dark matter simulations predict slightly or different spatial morphologies, but the key point is that all these simulations of all these dark matter simulations predict spatial morphologies that are distinct from the triaxial boxy bulge morphology. We have used basically all these different maps for the dark matter and for the stellar distribution, and we have found that the stellar maps provide a much better fit to the galactic center excess data. And that has allowed us to impose very strong constraints on the dark matter parameter space with the galactic center excess data. All right. So prompt gamma ray emission produced from the current sheet outside the light cylinder of millisecond pulsars can naturally explain the galactic center excess data. Now, the same millisecond pulsars are expected to accelerate electrons and positrons to very high energies. These electrons and positrons can upscatter ambient photons into higher energies, produce inverse Compton radiation that could potentially be observable by the forthcoming Cherenkov telescope array. So this is what we call the high energy tail of the galactic center excess. So the expected inverse Compton signal from this population of millisecond pulsars in the center of the galaxy. So we have run the tail simulations of this inverse Compton signal. For that, we have used GalProp. We have simulated a population of millisecond pulsars in the center of the galaxy following different spatial morphologies. Here we use a spherically symmetric morphology, and here the boxy bulge morphology. And what's interesting is that we have found that the inverse Compton maps are morphologically different depending on the spatial distribution of the cosmic ray accelerators, in this case, the millisecond pulsars. Now, what we want to find out is where these expected differences are large enough to be detected by CTA. This is the core focus of our project. So for this analysis, we used the instrument response function that has been generously made publicly available by the CTA collaboration. We have assumed a region of interest of size 10 by 10 degrees. We have masked the galactic plane and also some very bright sources in our region of interest. We assume 500 hours of exposure time, and we use the energy range between about a few GeVs to a few hundred TeVs. All right. For the statistical pipeline, we use the bin by bin analysis that has proven to be very successful in analysis of Fermi-Lat data. Now, these are the specifics of the astrophysical background. Since we have not yet observed diffuse gamma rays in this large region of interest at the TV energies, we are required to run simulations of the astrophysical background. And we do that using Galprop, the latest version of Galprop. We use the model proposed by Johansson et al. 2018, which is in agreement with multi-messenger cosmic ray observations. And these are the results for the hadronic gamma rays, and these are the results for the inverse Compton gamma rays, and these are divided in different galactocentric rings, which is something that is very useful when analyzing real data. Now, for the Fermi-Boltz component, we have used an extrapolation of the best fit model to Fermi-Lat observations. Since this component is quite uncertain at low latitudes, and we have not observed it yet at the TV energy range, what we do is we have two different models, an optimistic scenario and a conservative scenario. And these two scenarios are expected to encompass the range of uncertainties for this component. Now, for the signal component, we also use Galprop to simulate the expected inverse quantum signal from this population of millisecond pulsars in the center of the galaxy. And here I note that the luminosity in electron and positrons that are injected by these millisecond pulsars can be written in terms of the millisecond pulsar spin down luminosity. This proportionality factor, it's called the electron-positron acceleration efficiency. Now, a similar equation can be written, but now for the gamma ray luminosity. So that means that we can find a relation between the electron-positron luminosity and the electron-positron acceleration fraction. And so that will allow us to make physical interpretations of the CTA sensitivities for the signal, because interestingly, this fraction can be measured independently in millisecond pulsars in the field. Now, in our simulations, we run different injection spectrum for the electrons and positrons because this is very uncertain. We use different parameters that are supposed to encompass also the range of theoretical uncertainties for this component. Now, this is a summary of our pipeline. We have here all the astrophysical background. We have here the signal component. We convolve this with the instrument response function, then Poisson fluctuate those results, and then create mock data. Now, we fit the mock data with two different scenarios, an optimistic scenario and a conservative scenario. In the optimistic scenario, we fit the data with exactly the same model that we use in the creation of the mock data in the first place. In the conservative scenario, we fit the data with a completely independent astrophysical model. So that basically mocks up a scenario in which we don't have a perfect knowledge of the astrophysical background. All right, these are the results of our analysis. So we have here for the optimistic scenario, we inject the signal with different luminosities, and then we try to see where the pipeline successfully recovers the injected signal. So we are injecting a millisecond pulsar inverse Compton signal here. This line here shows the detection threshold for the millisecond pulsar signal, and we see that above the detection threshold, the pipeline successfully recovers the injected signal. Now, in the conservative scenario, in the case where we don't have a good model for the astrophysical background, we see that there is a decrease of the detection sensitivity, but again, for luminosities larger than that, the pipeline successfully recovers the injected signal. Here we see the minimum fluxes that are required for a successful detection of this inverse Compton signal by CTA. And here we show the minimum electron-positron acceleration fractions for different injection spectra, which is shown also in this table, and for the optimistic scenario, conservative scenario. So any values above these ones that are shown here should be detected at 5 sigma significance with CTA. Now, what's interesting to notice is that all these values, most of these values are physically plausible, except this one here for this injection 2, which is very similar actually to the astrophysical background. So even in this case, it might be possible, given substantial uncertainties, theoretical and observational uncertainties on this parameter, it might still be possible to make this potential detection compatible with millisecond pulsar modeling. So for the last task, we wanted to see where CTA could distinguish between dark matter and millisecond pulsars, or a spherical distribution of MSPs and a boxy-hole distribution of MSPs. And what we observed here is that, so we injected a millisecond pulsar signal and then tried to record that with dark matter and millisecond pulsars. And we see that the pipeline successfully assigns the flux to the millisecond pulsar component, which is very encouraging. All right, so these are the conclusions for my talk. CTA will be able to prove the millisecond pulsar hypothesis for the galactic center excess for physically plausible electron-positron acceleration efficiencies. And also CTA can disentangle a millisecond pulsar component of a dark matter component. And as a technical note, we have also found that the statistical pipeline that has proven to be very successful in analysis of Fermilab data can also be successfully applied to CTA data. Thank you very much.